Hi, I'm George Woodbury from College of the Sequoias, and it's CSI time. We're going to take a look at Newton's law of cooling to try to figure out the time of death for a body found in a refrigerator. Anyway, Newton's law of cooling says that the rate at which a body cools is proportional to the difference in temperature between the body and the environment around it. Now, that can be a human body, or it could be like a bowl of soup, a cup of coffee. It cools down much quicker at the beginning, and then the rate starts to slow as it gets closer to the temperature of the environment around it. So it moves quickly towards it, and then it starts to slow down as it approaches it. The model is is f of t equals t sub 0 plus c e to the negative kt power. And it's similar to the exponential models we've been using, except for that constant that's added on, that T sub 0. T sub 0 is the temperature of the environment. C is a constant which has to do with the difference between the environment and the body at first measurement. K is the rate at which the temperature decreases, and T is the time. And here, the problem we're going to work, T is going to be the time in hours. So we're told that a human body is found inside a walk-in refrigerator at a restaurant, which is kept at 35 degrees. The temperature of the body when it was discovered is 96 degrees, and 1 hour later, which will be on the worksheet that you have in front of you, the temperature has dropped to 95 degrees. We want to find a function that will model the temperature of the body. And so what we know is when T is 0, right, when we found the body, the temperature was 96. So 96 degrees equals the refrigerator's temperature, 35, plus C times E to the negative K times 0 power. That's going to be E to the 0 power, and that is equal to 1. So we're left with 96 equals 35 plus C. When we subtract the 35 over, that constant is 61. So again, it's just the difference between the environment and the initial temperature. So updating our model, f of t equals 35 plus 61 e to the negative kt. And we want to solve for k. We want to find out what that rate is. And that's where the part that I had left off when I originally typed this is really important. 1 hour later, at time when t is 1, the temperature is 95. So we can substitute those two in to figure out what k is. 95 equals 35 plus 61 e to the negative k times 1. Negative k times 1 is just negative k. Subtract over the 35 first, and we get 60 equals 61 e to the negative k power. Divide over the 61. 60 over 61 equals e to the negative k power. Take the natural logarithm, Sorry about that. Take the natural logarithm of both sides, and we're left with the natural logarithm of 60 over 61 equals negative k, or k is the opposite of the natural logarithm of 60 over 61. Oh, sorry. That is not helping. There we go. Time to go to the calculator. We're going to round this like we've been doing all along to 6 decimal places. Negative function natural logarithm back to the main of 60 divided by 61. And we get 0.016529 for k. So we've found our model, and let me rewrite the model one last time. F of t equals 35 plus 61 e to the negative 0.016529 t power. That is the model, and that will let us solve any sort of problem where we know the time or we know the temperature. If we know the time, we can get the temperature. If we know the temperature, we can get the time. Part B says, if the body is left in the refrigerator, what will be the temperature? What will the temperature be in 6 hours? So that's 6 hours after the initial. So T equals 6. And what we want to figure out is, what is that temperature? Okay. So this is just a basic evaluation of the function. We need to figure out what f of 6 is. And that's 35 plus 61 e to the negative 0.016529 times 6 power. Let's go to the calculator to do that. 35 plus 61 times function e to the x. And here's where we're going to type in that negative value of k times 6 power. So that's negative, back on the main, negative 0.016529 times. So notice what happened there, because I didn't use parentheses, it's dropped the multiplication down instead of being in the exponent. So let me go back and put parentheses, negative 0.016529 times 6, much better. And there we get 90.2 degrees. Right. Part C, we're going to work backwards a little bit, go back in time to try to figure out the time of death, assuming that the person had a normal body temperature of 98.6 degrees. So again, how long before the discovery was the body's temperature 98.6 degrees? Again, an estimate of how much time had passed before the body was actually discovered. So our model, f of t equals 35 plus 61 times e to the negative 0.016529 times t power. Here, we know the temperature, that's a function value. So that goes in on the left-hand side, and we can solve this equation for t. First step, subtract over the 35. (63.6) equals 61 e to that power. Next, we need to isolate the exponential part, so divide over the 61. To get the variable out of the exponent, we'll need the natural logarithm of both sides. That will leave us with just the exponent on the left. So the natural logarithm of 63.6 divided by 61 equals negative 0.016529t. And we just need to divide that over. Like that. And we'll use the calculator to figure out this last part. T is going to give us a negative time, and so we can subtract that backwards to figure out how long ago before the discovery the body was no longer a living body. Function, natural logarithm. Back to main, 63.6 divided by 61 tab outside the parentheses, divided by negative 0.016529, and we get approximately negative 2.5. So that's about 2.5 hours before discovery. So that's the way that we could. That's the way that we work with Newton's law of cooling. Again, it applies not just to dead bodies in refrigerators, but things like a cup of coffee, how quickly that will decrease in temperature over time to approach the temperature of the room that it's in. All right, that's the end of this section. I will see you. It's also the end of this chapter. I'll see you in the next chapter. Thanks.